Okay, so we're going to change it up a little bit here and talk about testing of BMS electronics for production. So in this presentation, I'm going to give an extremely brief BMS tutorial and go over some of the traditional manufacturing test methods for BMS and for printed circuit board assembly type of electronics. And then I'm going to present our universal approach to BMS testing. And along the way, I'm going to give 4 or 5 manufacturing test best practices. So first, a few quick facts about Bloomy. We provide BMS test equipment for the entire life cycle of the BMS product design. And that starts with the proof of concept to hardware prototype testing, and then firmware development and software regression testing using BMS hardware in the loop type of test equipment, as well as validation and verification of environmental as well as performance specifications of the BMS through to production test and return types of testing. We're a National Instruments Platinum Alliance partner. We've been in business for 25 years and we're ISO 9001 certified. Now, at last year's conference, I presented on firmware development testing using BMS hardware in the loop type of test equipment. And this presentation is significantly different. This is on production testing, but people always associate at this conference BMS testing with hardware in the loop. So if you're interested in hardware in the loop, we do have a demo of that in our booth. So, feel free to stop by if you'd like to talk about that. So there's 2 main topologies of the BMS, and one of them is centralized. And that's when you have a one or a few PCBs that are centrally located that perform all of the BMS's functions. And in the centralized architecture, you usually have a pretty significant wiring harness providing all of your cell monitoring and other wires up to all the individual cells from the central BMS. So the wiring is more extensive, more complex, more susceptible to noise, and also the BMS itself requires much more isolation because it's sitting on top of all of those cells. And then there's a distributed BMS architecture where you've got a slave board that is responsible for monitoring the individual cells or groups of cells as modules. And it monitors the current voltage and temperature, of those small groups of cells. And then it communicates back to the master controller what all of those cell values are. And the balancing is usually performed at the module level by these slave boards. And so the benefits of the distributed BMS, which is pretty much the dominant design and for a lot of applications, including hybrid and electric vehicles, as well as energy storage systems. So it's more noise immune, and the slave boards require less isolation because they're only exposed to smaller modules of cells and not the entire pack. And then the master controller is responsible for things like monitoring all of those modules, monitoring the pack overall voltage and current, and opening the main contactor if there's any kind of a problem. All right, so in addition, there's a continuum of variations in BMS topologies between centralized and distributed. So that's important to note. There are many different types. And that equates to many different BMS PCBA designs. And due to the various topologies, due to the different series and parallel cell, module and pack configurations, due to the many revisions that usually go into one BMS design for a particular vehicle program or so forth. You usually start with a prototype, an alpha, a beta, a gamma, and then a production boards. And all of those different boards are usually have significant differences. And what this means is that it would be worthwhile to have very flexible manufacturing test equipment for handling all of these different designs. And in addition, if you could test more than one vehicle program or ESS with the same test equipment, even better. All right, so traditional manufacturing test approaches include, first of all, in-circuit BMS PCBA testing. This is a process where the components that comprise the printed circuit board assembly are individually contacted and tested to ensure that each of the components is present and each of the components is functioning properly. Now, in-circuit testing is very widely used, very popular at all of the contract manufacturers, engineering manufacturing service providers usually have this equipment, and it's very good equipment. But it does not capture all of the defects. It does not capture whether all of these components are integrated and communicating properly, whether the software is tuned properly, whether everything is receiving power and the conductors are applied properly and the connectors, and that everything is working together is not assured when all of these components are tested using in-circuit testing. And that's a big risk, especially for a complex piece of equipment that, that has hardware and software like a BMS with control algorithms and such. So that's a risky proposition of relying just on in-circuit testing. And then there's battery module testing, where the modules are tested after they've been assembled together with the slave BMS board. And if you wait until the module before and then test, and then you find a defective BMS, it becomes much more expensive to repair that module and replace the defective BMS. And then there's full pack testing. And with pack testing, if the defective BMS gets all the way to this point, then there are safety issues with that pack, and there's higher voltage and current levels associated with it, and more expensive and destructive types of outcomes with the defects. So, best practice number one is to perform 100% PCBA functional testing prior to your module and pack assembly. So some of the functions of the BMS that in the corresponding functional test requirements that we recommend is first, monitor the cell voltages, currents, and temperatures, or that functionality of the BMS. Very important because the accuracy of those measurements relates to the accuracy of your state of health and state of charge estimates and all those good things. Okay? So your test system needs to simulate cells in order to accurately verify that the cell monitors are working. In addition, you can calibrate the cell voltage and current monitors in your functional test system. And that corresponds to usually deriving some coefficients that you would download to the FPGA or the PIC microprocessor or somewhere on the BMS. Okay, and then the next BMS function to test functionally is the cell balancing function. And in order to test that, you need to simulate out of balance cells with your BMS functional test system. And that's a particularly difficult one because simulating out of balance cells, you know, the BMS, the battery cells will sink in source current. And most commercial off-the-shelf power supplies, for example, won't sink in source current that way. Next BMS function is to monitor pack voltage, current, and temperature, which is generally higher voltages and currents. So the test system must supply high voltage and simulate high current and temperature. And then trigger alarms and safety interlocks in order to test that all of those are working, and in order to test that the BMS will open its contactor if there's a problem. And so the functional tester should simulate those alarms and faults by simulating over and under voltages, over and under current, and over and under temperature on each and every individual cell. Simulate opens and shorts on each cell, and verify that all of these alarms and safety interlocks are triggered on the BMS. And then finally, the BMS must communicate digitally to the ECM, charger, thermal system, other ECUs, etc. And so the test system needs to simulate or provide CAN communications or SPI or LIN or Modbus or whatever is necessary in order to test that functionality. So some issues with traditional printed circuit board assembly functional test is, so a few approaches that are common with this is functional test equipment. Unlike in-circuit test equipment, functional test equipment is often much more customized. Of course, manual bench testing has issues with operator subjectivity, repeatability, traceability, and most important, throughput. And so then there's also custom automated test equipment, or ATE. And this equipment is traditionally designed to be dedicated equipment for a specific PCBA or module. And there's a lot of companies out there that don't have the foresight to take into consideration the needs of multiple vehicle programs, multiple BMS boards, and really design a highly flexible type of BMS test system. So these systems are often inflexible because they were designed with one or a limited number of boards in mind. Battery simulation is a particular headache for people. A lot of people go in and they either try to use traditional commercial power supplies, which don't sink in source current, and that creates headaches for people. Sometimes you end up at a dead end with that. Or you end up designing a lot of custom circuitry, and then your test engineers become, you know, electronic design engineers, or end up spending a lot of time maintaining this test equipment. And that distracts them from their core focus of testing BMSs. And then, of course, the difficulty in modifying and maintaining the custom automated test equipment. So I propose the universal approach to BMS testing. Bloomy has a standard platform called a BMS Manufacturing Test System that is based on this system, but it utilizes a lot of commercial off-the-shelf components, and some of our customers have developed these themselves. So the information I provide here is not, proprietary or specific to Bloomy. So first of all, it's a functional PCBA test system consisting of a 19-inch rack of programmable test instruments, a mass interconnect fixture receiver, and interchangeable fixture heads. One universal BMS test system can test many different BMS PCBAs by simply swapping out the fixture. Okay, so it has fast turnover. Of course, you have to have different test programs for each BMS, and that's assumed. All right, so the software. So best practice number 2 is use commercial off-the-shelf software and hardware, and that reduces development time, effort, cost, and maintenance. At Bloomy, for our BMS Manufacturing Test System, we use National Instruments LabVIEW and Test Stand, and on top of that we have our own software that we call the UTS software suite, which out of the box allows you to have a standard operator interface and hardware and measurement abstraction so that you can interchange different instruments as needed from different vendors. Commercial off-the-shelf hardware, including specialized hardware that Bloomy has that is commercial off-the-shelf, and it is designed specifically for these unique challenges of BMS testing. And this includes the Battery Simulator 1200, which has 12 independently programmable cells that sync and source current under the BMS's control, which helps you test the cell balancing as well as the various faults. And additionally, 1,000 volts of channel-to-channel and channel-to-ground isolation allows you to connect many of these in series in order to simulate a larger pack. And it's FCC and CE certified. We provided this to as a kind of a shrink-wrapped commercial product off the shelf to customers in North America, Europe, as well as Asia. In addition, this year we've added a Battery Fault Insertion Unit, which adds 24 channels of 4-wire switching that allows you to apply a short to rail or an open circuit on any cell channel, and also connect a very high accuracy DMM for microvolt level measurements on any channel. So the connectivity, best practice number 4, is utilize a mass interconnect fixture receiver with interchangeable fixture heads. So we go off the shelf with this approach as well. At Bloomy, in our BMS manufacturing test platform, we use Virginia panel mass interconnects. There are other vendors including Mac panel, and these systems are great. What they do is they allow you to connect any test fixture to the base test rack and all of the instruments in it. And what this does is it makes that base rack very flexible and reusable for many different PCBAs under test. Okay, so summary of our manufacturing test best practices. Number 1, perform 100% functional testing of the BMS PCBAs. This increases quality in yield and reduces cost of fixing modules that have been assembled with defective BMS boards. Number 2, utilize commercial off-the-shelf hardware and software, including the available specialized battery simulators and fault insertion units designed specifically for BMS testing. Number 3, utilize a mass interconnect and interchangeable fixture heads, which makes your production line very flexible and able to swap out test boards very quickly. And I'm going to add on this slide best practice number 4, standardize on the universal approach. Many of our customers prefer to procure 2 of these universal systems One, they provide to the contract manufacturer to make sure that all of their boards are tested before you receive them in, and or before they're assembled with the module and pack. And additionally, the OEM likes to have one in engineering as well, so that they can retest any returns or any concerns that you have with a BMS, with a battery or a pack or a module that you want to take apart. You can retest it using the exact same equipment that your CM used and correlate your measurements in test results with what the CM tested. And finally, improve quality and reduce cost. Thank you very much.